Hello there, welcome to a presentation I've entitled Seamlessly from Functions to Equations. By the time you look at this presentation, you must be somebody who's familiar with functions, plotting of functions on system of coordinates which look as follows. So in this case, our generic notation of functions is given as y is equal to f of x, where x is the independent variable and y is the dependent variable. And the notation itself simply communicates that we can graph these functions on a system of x, y coordinate, which is a system as we can see here. So now, we also by now you should be familiar with solving simple equations, especially the first equations we deal with, which are linear equations. But in general here, what I want to discuss is to show you that functions and equations are almost one in the same chapter, because there are no equations without functions, or there are no equations really which are not related to a certain type of function. For example, if I was given this graph as a function y is equal to f of x, what we start with when we deal with functions, we start with evaluating functions, which in this case here we can simply say f at 0 is equal to 2, seeing that at here where x is 0, the value of the function is 2, meaning that the point 0.2 is actually a point on the graph of the function f of x. So then in this case, if really we didn't know that the value is the value of the function at 0 is 2, but we know that the function at some point attains the value 2, we would simply state here and say f of x equals 2 to 2. In other words, we already have the value of the function, but we don't know what is the value of x. But because we're in the presence of the graph here, we can simply go to the level 2 of the function, which is here, and then point downwards here, we'll be pointing at the solution. For example, if we had a value k there, and the value k here, and then we draw horizontally, and then we intersect the k of the function there, then if we go vertically down there, we'll be pointing at the solution of the equation f at x equals to k. For example, when we get here, we can see that the value of the function f at x is equals to 0, because the function is at a level 0 along the y-axis. But as you can see in this case here, we could simply say now here x is equals to minus 4. That in this case will be solving the equation graphically, because we're in the presence of the graph. Now, and the idea I'm showing you here now, that if you have got we're in the presence of a linear function like this, which is mx plus c, we also have got what we call linear equations, which normally come in this form, for example, as 2x plus 1 is equals to 5. That will be a linear equation. But what that means basically, that if we've got a function like this, we know the value of the function is 5, it's a linear function. So what do? We draw a horizontal line across 5. Then when we are there, what we have here is simple the coordinate y of the point, which is 5, but we don't know what the coordinate x is. So graphically, by drawing a vertical line here, we would end up more or less pointing at the solution of the equation there, which you would say in this case maybe it's 1 comma something. Or so in this case, we know that in this when we solve this equation, what we do basically, we do manipulate this equation using our knowledge of operation numbers. In this case, we say 2x plus 1 minus 1 equals to 5 minus 1, because our target is to end up here with x equals to x as a subjective formula equals to some number here. When we are here, we see that our main obstacle before we can talk about x is to deal with this minus 1. So using properties of numbers like a plus minus a equals to 0, and that a plus 0 is equals to a. So what we do here, we simply use this to create a 0 here by adding minus 1 and also adding minus 1 on both sides, because this is an equation we want to maintain it balanced. So definitely you're going to get 2x plus 0, which is going to give us 2x according to this property. And then this side we're going to get 4. And then we end up here with 2x equal to 4, which in this case again here we're going to divide both sides by 2. Then we get x equals to 4. Then we'd say we have solved the equation. So you can see that now what I'm trying to say here now, these linear equations we've played around with many times are actually linear equations which are related to functions which we call linear functions. In this case, the linear function here will be simply y equals to f of x equals to 2x plus 1. So when we are given the value 5, then we're simply looking at that level 5 and say at what value of x is the function going to reach level 5 along on the graph. So then from linear functions, we know that we normally deal with quadratic function. In this case, linear function, you can see here the power of x here is 1, and then when you get to quadratic functions, the power of x will be dealing with x squared, which will be the highest power in the function, and then we have got something which looks like this. We know that a quadratic function can be generally represented this way as a times brackets x minus h squared plus k, where x again is independent variable, y the dependent variable, and the h is the horizontal shift, k the vertical shift. So all this must be understood before you can actually say you understand almost everything about quadratic function. And then hk will be the turning point of the parabola, which is actually the name given to the graph of the quadratic function, which will be somewhere there. Turning point, why? Because as you can see from the left to the right, the function is decreasing, and when it gets to that point, it starts increasing. Then we call this a turning point. So the turning point is given by these coordinates there. So when you look at this equation in general like this, you must be knowing that this h and k will give you a turning point. And actually the equation x equals to h, which is an equation of a vertical line, actually represent the line of symmetry of this parabola, because we know that the parabola is normally symmetric around a vertical line. If it's the standard parabola like y is equal to x squared, we know it's going to be symmetric around the y-axis, which in this case, this parabola, if you wanted to write it this way, would simply say this is 1 multiplied by x minus 0 squared plus 0, where in this case we'll be simply saying our h is equals to 0, our k is equal to 0, then 0, 0 becomes the turning point, and the x equals to 0 becomes the line of symmetry. So talking about symmetry, then we can look at this graph. We can look at this. A parabola can be positioned this way, or normally as just a parabola around the y-axis here. So if it's shifted horizontally like this, if we look at this graph here, we would say the turning point is 1,5, which is 3 halves, comma minus 2. And then writing like this, we know that this is the equation of parabola. And we must also know that at the end of simplification here, if we simplify this, we end up with an expression which looks like this: ax squared plus bx plus c. Just see how you can do that with this and get the equation this way. So then if we end up, let's say for this parabola, taking, let's say, some level here, which we can also call, let's say, this is level D, and then we wonder at what value of x is that level going to be reached by the graph of the parabola. Then was simple, by so doing, was simple setting up an equation, and then when we're multiplicating this, you can see that we can end up having, by subtracting d here on both sides, and then we say we've got a quadratic equation. In this case, the quadratic equation basically will have two solutions. As you can see here, the power of x is 2. You can have two solutions, which will be somewhere there and somewhere there. So what I'm doing here with this sketch is just I'm illustrating how you could sort of visualize the positions of the solutions to the quadratic equation. Now coming back to this equation, which you can see here, like this one, you can see definitely here that our k is equals to minus 1, as you can see it here. And the line of symmetry looks to be 0, x equal to 0, because there from there to there, we've got equal distances there. So which means our h is equals to 0. So then if we were to now want to know where is this graph 0, what we'll simply do is we'll say here a brackets x minus 0 squared minus minus 1, which is or let's say plus minus 1, which is our k, equals to 0. then we'll be simple there is asking ourselves, where does this graph cast the x-axis? But as you can see on this graph, we can see that the graph casts the x-axis at -1 and 1, which will be the solution of that equation. So as we know, the solution of quadratic equations, we can find them by factorizing or using the formula, or even using graphs. If we can draw a graph accurately. So the other thing which we need to know now in general, now when we come to other functions like trigonometric functions, exponential functions, which we have discussed, we need also to remember, we need also to have the idea of the inverse function, which we said if we've got f as a function, the inverse function will be denoted as f to the power -1 there, and we read that as y is equal to f inverse. And talking about that, we should know also this fact that if we now compose a function and its inverse in any order, what we get here is the identity function. In this case, what we're going to get here, this is going to be equal to x. And I said before that this now, we can actually consider it as a kind of a device for solving any type of a function, depending which type of function you are dealing with. So if you compose a function and inverse, you get that. For example, let's look at an example of an exponential function. Let's say we've had an exponential function like this. In this case here, this is an arbitrary base a. We can now consider that let's say a is equal to 2. We'll be having a function like 2 to the power x. Now let's say at some level, we select a level there. Let's say you can even set it to be 64. And then if you want to know now with what value of x is the function 64, you'll be simply setting up an equation saying 2x equals to 64. And then now we know that we've already discussed this and said if we've got an exponential function, we know that the inverse to that function would be a logarithm function, which you denote as y is equal to log base 2 of x. That will be the inverse function. So we can pair now y equals to this f of x, and pair it with y is equals to 2 to the power x. Now this is f inverse of x. So now if we've got this equation, we actually want to now starting from 2 to the power x equals to 64, we can now do this and say if we want to x, we can simply apply the inverse function to this one and end up having here log base 2 of 2 to the power x equals to log base 2 of 64. And applying properties of logarithms, we know that we can end up with x log base 2 of 2 equals to log base 2 of 64. Now, knowing the fact that log base a of any log base a of a is always equals to 1, then what we have here, we end up with x equals to log base 2 of 64. Now, if you have this, you have practically solved the equation for x, except that you can leave it like this in terms of logarithm if you are not asked to calculate it to any decimal places. But otherwise, you must note also here that you don't have log base 2 on the calculator, and then this also motivates now the knowledge of knowing the change of the formula for change of base, which we noted that if we've got log of m to any base a, you can change this to a base of any choice. Like by doing this, you say log of m base of your choice over log base c again of a. Then you can now answer this. So in this case, since on the calculator we're given base 10 and the natural base e, we can simply find the actual value in decimal notation by just simply calculating log base 10 of 64 over log base 10 of 2. Then we get that. You can try this. You can see that even if you move you use an alternative base like the natural base, you will get this as a ln of 64 over ln of 2. But otherwise, if you're not asked to give this answer to any decimal places, you can leave your answer in this form. By then, you should have shown exactly how that you know how to solve an exponential equations, the exponential equation of this form. So now, you recall that the types of functions we've looked at exponential functions. In this case, we pair them with logarithm functions of corresponding base as inverse. We also looked at trig functions, trigonometric functions, and also we have their inverses, inverse trig functions. And what is important here is that for any type of function you deal with in terms of dealing with the related equations, you will always need to remember this type of relationship, which says if you compose a function with its inverse, you actually get the identity. Because in this case, if you're just like, let's say, given a sine of x equals to 0,5, in order to know what is x is here, you will simply need to make x substitute formula, and there's no way you can do that except by invoking the inverse function sine there, and then on the other side you say inverse function sine of 0,5. Then you can now use a calculator to determine the value of x. So what I'm trying to illustrate here is that, guys, when you're dealing with equation, never overlook the type of function you are dealing with in that particular equation. Then you can proceed very, very easily. So now let's just take one or two examples of equations and try to solve them. Now let's say you are given, in this case, e to the power 2x equals to 7. This is the simplest equation, which maybe no one is going to give you for any kind of evaluation or what, but I want you just to start from the simplest, then we can see how we can complicate this just to sort of give more challenging problems related to this. So in this case, if we've got this, we must know that what we need is to have x equals to some number. So now what we see here, we see that what we're dealing with here, we're dealing with the function e, let's say e to the power of x. So immediately when we do this, we must recall that the inverse to this is ln x, which you should recall that this simply means log base e, the natural base e of x. And then for these two, you must know that ln of e to x is equals to e to the power ln of x, which is equals to x. So in this case now, if I want to have an argument x here, and I want to free it from the exponential function there, what I need to do, I need to call upon ln. Same way, if I've got an argument x as an argument of ln, if I want to free it, make it independent as an argument there, I need to call upon e. So when I get to this equation, you will simply say here ln of e 2x equals to ln of 7. That's what we must do with equation. Whatever you do on one side, you do on the other. So applying properties of ln here, we'll end up with 2x ln e equals to ln 7. And then ln e simply says log base e of e, which we know that this is equals to 1. Then we end up here with 2x equals to ln 7. And then at the end, now we can just simply say, therefore, x is equals to ln 7 over 2. That's what we've got there. Then from there, if it's necessary, you can then go to the calculator and press ln 7, then you get this number in decimal notation. But like I said, normally this is just an initial part to start examples, but you get more challenging problem than this. For example, we can get something like this. Let's say we've got e to the power 2x minus 5x minus 5e to the power x plus 6 equals to 0. Now, when you get to this kind of equation, you must look very carefully. This equation is actually what we can call a kind of a compound equation, which in this case is involving both exponential functions and the quadratic functions. How do I see that? Of course, I see that depending on the experience I've got on these things. If you look at this expression here, is simply e to the power of x squared minus 5e to the power of x plus 6 equals to 0, which essentially this equation is a quadratic equation involving an exponential function in this way, which if you were new in this thing, we could simply make a kind of a substitution here and just say, let's take e to the power of x be equal to some k, and then we end up here with k squared minus 5k plus 6 equals to 0. So what we can do there, if we can factorize, we can factorize. If we can't factorize, then we might resort to the quadratic formula to solve for k. And then once we solve for k, we'll be back to that type of equation we started with, which was e to the power of 2x equals to 7. Then we simply apply the procedure we did there. So in this case here, when we factorize, we get something like this. I'm not going to use k, I'm just going to look at this e to the power of x here as k, and factorize this as e to the power of x minus 2 multiplied by e to the power of x minus 3 equals to 0. So at a point whereby you've got two numbers a times b equal to 0, which you know that this means a equal to 0 or b equals to 0. Then if that's the case, you simply say e to the power of x minus 2 equals to 0, or e to the power of x minus 3 equals to 0. Then in this case now, we can now simply make e to the power of x subject formula in order to arrive at an equation of this type. In this case, by adding 2 on both sides. If we add 2 on both sides here, we will simply get e to the power of x equals to 2. And we know the graph of e to the power of x is a graph which looks like this. So it's 1 there, and it's growing. Definitely, then it's going to get to some level 2. Then the x we're looking for is some x which graphically can be pictured there. Similarly, we can do that for this one. So applying what we just saw before here, this would be simply saying this is equivalent to ln e to the power of x equals to ln 2. And then we know what we're going to get here. We're simply going to get x, and then we get that x is equal to ln 2. If we want it in decimal, then we get 2 to a calculator. Similarly here, we'll end up with e to the power of x equals to 3, and then we get the x equals to ln 3, applying the same manipulation we've just done here. But you've got to be very, very careful when you deal with this type of equations. Let's see the next example, and just to make sense of what I'm talking about. Okay, here's another example. Now, when you look at this example, it's similar to what we've just seen. And what I'm going to say here, please try to apply to other exponential situations of this kind. For example, if I were to factorize this, we end up saying e to the power of x here, brackets e to the power of x equals to 0. And then I hope you can see that this you can have as minus 3 here plus 2 there. Just double check that, you'll see you get to that. Now, if we now solve this equation, you'll simply say now e to the power of x minus 3 equals to 0, or e to the power of x plus 6 equals to 0. And then if you come to this situation here, you will see that you can add on both sides here plus 3, and then you get e to the power of x equals to 3. And then if you think here, you will think exactly similar way we did there, that the exponential function e will intersect the y-axis at 1, and then it will go this way. Then you expect it to be some level there, to be at level 3. Then we're simply searching for that x there, which that x will end up getting by applying ln on both sides here, and then end up saying x is equal to ln of 3, and then that will be your answer. But if you come to this case here, check what's going to happen here. If you add on both sides minus 6, to get e to the power of x equals to minus 6. And then if you reflect on this graph and the properties of the function e to the power of x, which we have discussed before, you'll notice that this is giving a kind of a contradiction, which is not acceptable. This function e to the power of x is always strictly greater than 0, though whether it's growth or decay, it is strictly greater than 0. So now here, this is saying e to the power of x is equal to minus 6. Definitely, even if you look at the graph here, you don't expect this graph y equals to e to the power of x to reach level minus 6. So what does it mean here? You can get an equation as it is here, but when you calculate, you must be very, very careful for such cases so that you can answer them appropriately. So in this case here, you would simply say this is not applicable because the exponential function has got the line y equals to 0 as its asymptote. So it will never cross it, so it will never reach minus 6 at some stage. So when you get this, so your answer here simply becomes this x, and you must indicate there that this is not applicable. So I think this example which I've talked about here, it just gives you a kickstart on how to deal with equations of different types. So we're going to continue this with this kind of practice. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Wasfani Msipa.